Hello, welcome to another module in this massive open online course on the principles of MIMO, OFDM and CDMA wireless communication systems. And we had seen in the previous module, there are different multipath components in the wireless communication channel. And therefore, corresponding to the ith path, the received passband signal component is the real part of AI times S of t minus tau I into e to the power of j 2 pi f c t minus tau I. So, now therefore, the superposed signal, therefore, the received signal is the sum of these multipath components. Received passband signal equals sum of equals the sum of the various multipath components, and therefore, what we have is we have yp of t equals sum of, that is the received passband signal equals sum I equal to 0 to L minus 1, the real part of AI times S of t minus tau I times e to the power of j 2 pi f c of t minus tau I, right. So, this is the received passband signal, which is the sum of the various multipath components, and I can further simplify this as I equal to 0 to L minus 1, the real part of AI S of t minus tau I e to the power of minus j 2 pi f c tau I times e to the power of j 2 pi f c t, that is the carrier component. You can clearly see e to the power of j 2 pi f c t, the carrier modulation component is common to all these paths. So, I can extract that as the common term, and now I can therefore write this as the real part of summation I equal to 0 to L minus 1 AI S of t minus tau I e to the power of minus j 2 pi f c tau I times e to the power of j 2 pi f c t. And now, if you look at this received passband signal, you can see that this is the carrier, this is the carrier component or modulation by the carrier, and this is the complex baseband part. So, this is the complex the part that I am indicating over here, which is the sum I equal to 0 to L minus 1 AI S of t minus tau I e to the power of minus j 2 pi f c tau I, which is the sum of the attenuated and delayed baseband signal. This is the complex received baseband signal, and therefore, my baseband received signal, if I remove the demodulate the carrier, the baseband received signal is given as summation I equal to 0 to L minus 1 AI S of t minus tau I e to the power of minus j 2 pi f c tau I. All right. So, this is my complex baseband this is the complex baseband, this is the complex baseband received signal, that is y of t, which is, and you can see this is the sum of the several multipath components. The ith component is AI S of t minus tau I e to the power of minus j 2 pi f c tau I, and therefore, this delay tau I is giving rise to this complex phase factor. You can see this delay tau I, the ith delay is giving rise to the complex phase factor. This is giving rise to the complex phase factor. What we are going to do now is to further simplify this slightly. What we are going to do is we are going to employ what is known as the narrow band assumption. So, we employ the narrow band assumption for the transmitted signal, which says that S of t minus tau I is approximately equal to S of t, and we can employ this assumption when we have a narrow band signal. What does it mean to say a narrow band signal? Narrow band signal means f of m is significantly less than the carrier frequency, that is the maximum signal frequency of the signal is less than the or significantly less than the carrier frequency. When we have this maximum signal frequency f of m significantly less than the carrier frequency f c, then we can employ the narrow band assumption. For instance, when we look at a GSM signal, the GSM signal has a bandwidth of around, the maximum frequency is around 200 is under 200 kilohertz, which is well less than 1 megahertz, but the carrier frequency FC is 900 megahertz. For GSM, you have FM is approximately equal to 200 kilohertz, while FC is approximately equal to 900 megahertz. The carrier frequency is approximately around the order of 900 megahertz. Therefore, the maximum frequency is of the signal is much lesser or much lower than the carrier frequency, and therefore one can employ the narrow band assumption in this case, where we are approximating this S of t minus tau I, that is the delayed baseband signal. S of t minus tau I is approximately equal to S of t. Now, if we employ this assumption that S of t minus tau I is approximately equal to S of t, what we have is this reduces to sum of I equal to 0 to L minus 1 A of delta A of, since S of t minus tau I is approximately equal to S of t, this reduces to AI S of t e to the power of minus j 2 pi f c tau I, which means employing the narrow band assumption, I have y of t equals sum of I equal to 0 to L minus 1 AI e to the power of minus j 2 pi f c tau I times e to the power of j 2 pi f c tau e to the power of minus j and times S of t times S of t, since S of t can be taken common from this expression, and therefore now you can see this is a complex coefficient. This is a complex coefficient let us denote this by h. So, h I am defining this as summation I equal to 0 to L minus 1 AI e to the power of minus j 2 pi f c t I. This is my complex coefficient, and as a result of this I can conveniently write y of t equals this complex coefficient h times S of t. So, this is my complex coefficient. So, y of t equals h times S of t, where this complex coefficient depends on the channel. It depends on more precisely the attenuation, comma, delay of different multipath components of the channel. Precisely, it depends on all the AIs and tau i's. So, this depends on the different multipath components, the attenuation factors AI's and the delays tau i's of these different multipath channel components. Alright. So, this complex coefficient H depends upon these different channel factors. Right. So, now let us try to understand this channel coefficient better. So, let us consider a simple scenario. L is equal to 2. For L is equal to 2, we have H is given as summation I equal to 0 to L minus 1, which is 1, A of I e to the power of minus j 2 pi f c tau I, which is A naught e to the power of minus j 2 pi f c tau naught plus A of 1 e to the power of minus j 2 pi f c tau 1, correct. And now what we have is we have the sum of two multipath components, that is A naught and A 1, that is H is given as A naught e to the power of minus j 2 pi f c tau naught plus A 1 e to the power of minus j 2 pi f c tau 1. Now, let us consider a scenario in which A naught equals A 1 equals 1. Let us consider a simple scenario with A naught equals A 1 equals 1 and tau naught equal to 0 and tau 1 equals 1 by 2 f c. In this scenario, what I have is H equals A naught, that is 1 times e to the power of minus A e to the power of minus j 2 pi f c tau naught, that is e to the power of 0 plus A 1, which is 1 times e to the power of minus j 2 pi f c tau 1, which is 1 over 2 f c, which is equal to 1 times e to the power of 0 is 1 plus 1 times e to the power of minus j pi, which is e to the power of minus j pi is minus 1. So, this is 1 plus minus 1, which is equal to 0. So, what we have is H, the channel coefficient, reduces to 0, and you can see that because both the components have equal amplitude 1 and they have a phase that is exactly the opposite of each other. One has a phase of 0, the other has a phase of pi, and therefore, these components are cancelling each other. As a result of these multipath components cancelling each other, the channel coefficient H is 0, and therefore, the received signal y of t, which is H times S of t, which is equal to 0 times S of t equals 0. Therefore, the received signal is perfectly cancelled, and this is a case of, this is an example of destructive interference, where these two multipath components are perfectly cancelling each other. This is a case of destructive interference, in which case the received signal is 0. So, in this case, this H is 0, this shows destructive, this is destructive interference. Now, further consider another scenario where again A naught equals A 1 equals 1, tau naught equals 0, tau 1 equals 1 by f c. In this case, you can see H is equal to A naught, that is 1 times again e to the power of 0 1 plus A 1, which is 1 times e to the power of minus j 2 pi f c times 1 by f c, and now it is H is equal to 1 plus 1 times e to the power of minus j 2 pi, e to the power of minus j 2 pi is 1. So, this is 1 plus 1 equals 2, and now you can see since H is 2, we have y t equals twice S of t, that is twice the transmitted signal S of t. And now you can see, because these two signals are adding up constructively, so they are adding up to each other constructively. So, this is constructive interference, and as a result of this you see an enhanced signal amplitude. So, this is basically enhanced signal amplitude. So, this enhances signal amplitude So, when these different multipath components they cancel each other, then you have destructive interference, or with these these two multipath components add constructively, it leads to constructive interference, and that enhances the signal amplitude at the receiver. And therefore, this coefficient h depends on the attenuations ai and the delays tau I. It varies between, it can go all the way down to 0 when these different signal components are cancelling each other, and it can, when different signal components add up, it can have a significantly higher magnitude, and then it varies between these different magnitudes. So, h varies, the coefficient h varies depending on the various channel amplitude or the various channel attenuation factors ai and the delays tau I, all right. And therefore, as these attenuations and delays are changing, the channel h, which if you remember the h, the expression for h is equal to summation I equal to 0 to L minus 1 ai e to the power of minus j 2 pi fc tau I. As these various delays ai and the attenuations tau I are changing, this channel coefficient h is also changing, and it can go all the way from 0 to have a very high magnitude. And therefore, if you plot this channel coefficient, this channel coefficient will have a magnitude that is changing with time. That is, if you are looking at the time, and if you are looking at the average, the power of the fading coefficient, the power of, or magnitude square power is so this fading coefficient is changing with time, and this changing with this process, that is why this is known as this coefficient, that is why this complex channel coefficient whose magnitude is varying with time, with changing with time, is known as the fading channel coefficient. This is known as the, this process is known as a fading, this is known as the fading process, and this is known as a h is known as the fading, and this is an important aspect of wireless communication systems. This is known as the fading channel coefficient. So, this process is known as fading, and this is known as h is known as the fading channel coefficient. And of course, as you can see here, sometimes when the paths perfectly cancel each other, the signal amplitude or the received signal amplitude goes all the way, can go all the way up to 0, or can go to a very low amplitude, as it is represented by this trough here in the power of the fading coefficient. This is represented, this particular point is known as a deep fade. This is known as a deep fade event, and this has a significant impact on the performance of a wireless communication system. We are going to look at all these aspects in subsequent modules as we proceed further, and we will see that this such deep fade events have a profound impact on the performance of the wireless communication systems. Therefore, it is the fading, therefore, this fading process which results from the multipath wireless communication environment. So, this fading process, or let me write it, this fading process So, this fading process is basically which causes the received power to vary. which causes the receive power to vary is an important and key aspect, is an important and key aspect of this is an important and key aspect of a wireless communication system. So, this is a very important aspect and it has a significant impact. It significantly impacts the nature of wireless communication, because as the channel coefficient is varying, the received signal power is varying, and as the received signal power is varying, the quality of the received signal at the receiver is changing. And this is unlike, and this is arising, remember, because of the multipath propagation environment in which these different signal components with different delays and different phases are superimposing, and this is leading to constructive and destructive interference. And this channel coefficient basically captures this constructive and destructive interference properties of the wireless communication channel, and this is significantly different from the wireline channel where there is no multipath propagation. Therefore, this fading coefficient has a significant impact on the nature of wireless communication, and it has a key role to play, and we are going to spend a significant amount of time trying to understand its properties, trying to understand its impact, and trying to understand how are the different technologies, how are the different solutions, what are the different solutions that have been proposed to overcome the adverse impacts of this fading wireless communication, fading wireless channel coefficient, which is a key feature of wireless communication systems in general. So, in subsequent modules, we are going to develop models for this fading channel coefficient. So, in the subsequent modules, what we are going to do is we are going to develop models for this we are going to develop models for this fading channel coefficient H, and based on these models for this fading channel coefficient, or in other words the model for the wireless channel, we are going to understand the various properties and performance of the wireless communication systems. So, we will stop this module here and we will continue in the subsequent modules. Thank you very much.